Hi, this is Kevin from the Mathsaurus, and this is question 11 of the Step 2 paper from 2019. It's a combinatorics and probability question, and it's a nice question in the sense that the question gives you some of the answers as you go along. That can be really useful as a check on your answers. If you do make a mistake, you can find it and correct it if it's just a minor mistake. Anyway, let's have a go at the question. Part 1, it says there are three integers n1, n2 and n3 that are in strictly increasing order, all positive, and the sum of the first two is larger than the third one. Find the number of ways of choosing these numbers when n3 is 9 and n3 is 10. So it's clearly a bit of a warm-up to the rest of the question here, but it will take us a bit of thought even in this case. But this first part is just meant to kind of get you used to the notation and the problem here. So let's just try this in the case n3 equals 9 to begin with. So let me just think about what n1 and n2 could be then. So they've got to be smaller than n3, n1 has to be smaller than n2, but together they've got to be bigger than n3. So okay, so the smallest n1 might be is 1, but then there's actually nothing that can go with it as an n2 because we'd have it to be bigger than n3 in total. This would have to be at least 9, but then n2 wouldn't be bigger than n3, so there's nothing possible here. But when n1 is 2, we could have n2 is 8, they add together to give 10, which is bigger than 9. For n1 is 3, we could have 7 or 8. When n1 is 4, we could have 6, 7 or 8, just making sure the total is at least 10 here, and that they're in strictly increasing order. N1 is 5, so okay, so 5 would work, but then n2 wouldn't be bigger than n1 here. So again, we can just have 6, 7, or 8. For 6, again, we can have 7 or 8, and for 7 we can just have 8. And then of course once we get to 8, there's no possibilities and there's nothing possible outside of that. So if we count these up, we get 1 plus 2 plus 3 is 6, and then exactly the same here, so that's 2 lots of 6 is 12 ways, okay? And we'll try the same thing for n3 equals 10. So the possibilities are n1 is 2 and n2 is 9, and we could have n2 is 3, and then this would have to be 8 or 9 to something. So somehow once we've done the first one, it's kind of easy because the logic is the same here, right? So for 4 it's 7, 8 or 9. Here we're just wanting the total to be at least 11, and for them to be in strictly increasing order. So for 5 we're going to have 6, 7, 8 or 9. For 6 we're going to have 7, 8 or 9. For 7 we'll have 8 or 9, and for 8 we'll just have 9 as the possibility, and then that's everything. So that's 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1, and that gives us 16 ways of doing it for n3. Okay, so this is really meant to be a bit of a warm-up and a guide for the rest of the question, right? So it now says, given that n3 is of the form 2n plus 1, so like the n3 equals 9 case, write down an expression that we don't need to prove for the number of ways of choosing the pair of numbers n1 and n2 and simplify it. Okay, so we look at what we've done in the first part and we say, okay, we don't need to prove this, so we don't have to be too rigorous here. What's the pattern, right? So it goes, I get one combination from the 2 here, then 2 and then 3, and then I get 3 more, then 2 more, then 1 more, right? So you can see, the n3 equals 9 case, if you like, this is 2 times 4 plus 1, right? That's 9. So in this case, n equals 4, and effectively what we get is 1 plus 2 plus 3, and then plus 3 plus 2 plus 1. So in general, I think this is going to work by doing 1 plus 2, and we stop at n minus 1, and then we do that in reverse. Okay, so actually that logic suggests that we just have to work out 2 times 1 plus 2 plus up to n minus 1, right? Now you might just know what the sum of the first n integers is, like 1 up to n, right? But really, so if I want to do, so let's just say if I effectively want to do the sum of n from n equals 1 to some capital N here. This is just an arithmetic progression with first term 1 and common difference 1, so it's just n over 2 times 2 times a plus n minus 1 times the common difference of 1, so it's a half times n plus 1. And again, perhaps you just know that formula for the sum of the numbers 1 up to capital N, right? So we want to do something like that here, but we just want to go up to n minus 1, so I've got 2 times a half times n minus 1 and then n minus 1 plus 1. Okay, so I get exactly this, so that's just n times n minus 1. Okay, that will be the number of ways of choosing this pair of numbers. Now it says write down and simplify the corresponding expression when n3 is 2 times n, right? So now we're going to look at the same thing for this case here, right? This one would be 2 times n, where n equals 5, and this time we get 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1, right? So this time we want the sum up to n minus 1 and the sum up to n minus 2. Okay, so it's going to be, again, we don't have to prove it because we can just write it down. So we can just do, we want the sum up to n minus 1 plus the sum up to n minus 2. Right, so again, that's a half times n minus 1 times n plus a half times n minus 2 times n minus 1, just using different instances of that same formula. So we can factorize here the n minus 1 and the half, and then I get n plus n minus 2, so that's 2n minus 2. So this is 2 times n minus 1 times a half times n minus 1, so that one just gives us n minus 1 squared. And I suppose we can just absolutely double check that that does match with our first answer here, right? n minus 1 squared here would be 5 minus 1 squared, which would be 4 squared or 16, and then this other one, n times n minus 1, would be 4 times 3 is 12. So we've got some checks as we go through this question that we're getting this right. Okay, so in the next part here it says we've got n rods of length 1 up to capital N, one of each length. We're going to choose for sure the rod of length n and then choose 2 more at random from the remainder, each of those choices being equally likely. And then we want to show that when n equals 2n plus 1, the probability that these rods form a triangle of non-zero area is n minus 1 over 2n minus 1. Okay, and I think some people get thrown off by the appearance of some geometry here, but we just need to think about when can we make a triangle out of 3 sides that have non-zero area. Well, obviously if these 2 shorter sides aren't at least as long as the longer side, then the triangle's not going to match up. But if this n1 and n2 are bigger than this side n3, right, then we get a good triangle. So you might want to say something to that effect in this question, but just to notice that this is effectively then related to the problem that we were looking at before. Okay, so it's the same structure as this initial problem that we want n1 plus n2 to be bigger than n3. Our n3 here is chosen to be this capital N, okay, we need to think carefully about whether we want to do n1. So we definitely need n3 is bigger than these 2. Do we also need that n1 is less than n2? Well, we can just choose it so that we do have that, and it will match to the first part of the question, right? So when n equals 2n plus 1, then, right? So firstly, let's just say, so how many ways are there of choosing the remaining remaining 2 rods, regardless of whether they make a triangle, right? So we're going to have n. We've definitely chosen the one of length n, and we've got n minus 1 of them left, and we want to choose 2 of them. So we can just do n minus 1 choose 2. Now n minus 1 is 2n plus 1 minus 1, so that's just 2n choose 2 for the small n here. So that's 2n factorial over 2n minus 2 factorial times 2 factorial, and that's 2n times 2n minus 1 all over 2 if you think about everything cancelling here. So this just gives us n times 2n minus 1, right? And the fact that I've done this using choose 2 means that I'm going to retain this condition n1 less than n2, because I'm not counting like both the possible orderings, right? I'm just counting the choice of, you know, like lengths 3 and 5 once. I'm not counting here 3 and 5 as well as 5 and 3. So we've seen earlier that the number of you know, possible or valid here triangles, right, in the case 2n plus 1, right, that was this part here, that was n times n minus 1, right, from above. Right, so actually the probability that when we pick this one at random we get a possible triangle, so the probability that a triangle is possible from the 3 rods that we've chosen is just the number of triangles that are possible, n minus 1, out of the total number of ways of doing this, n times 2n minus 1. So the n's cancel here, and I get n minus 1 over 2n minus 1, which is exactly the expression as required here. Okay. So, looking good. And now we just want to do the equivalent case when capital N is equal to 2 times n, right? Okay, so we'll do the same, you know, we'll do exactly the same calculation here. So, so the number of choices of 2 rods, well, it's still, as before, n minus 1 choose 2, but this time it's capital N is 2 times small n, so that's 2n minus 1 choose 2. Okay, so we get 2n minus 1 factorial over 2 factorial times 2n minus 3 factorial. You can jump through this a bit quicker if you can get to the simplified version. I'm just trying to be clear here. So on the top I get 2n minus 1 times 2n minus 2, and the rest of the 2n minus 3 factorial cancels here. 2n minus 2 is 2 times n minus 1, so I can cancel the 2 as well and get 2n minus 1 times n minus 1, right? And you know, the number of possible triangles that we found earlier in this case was n minus 1 squared. Okay, so the probability that a triangle is possible from the 3 rods that we've chosen is n minus 1 squared divided by 2n minus 1 times n minus 1, and we get a cancelling of the n minus 1, and so that gives us n minus 1 over 2n minus 1, and we just notice here that that's the same as in the previous case actually, so so we get the same formula in the 2 different cases. Right, okay, so almost there then, just one more part to this question, and it says now we've got 2 capital M plus 1 rods of lengths 1 up to 2 capital M plus 1, and we're going to choose 3 rods at random, each of those choices being equally likely, and we want to show the probability the rods can form a triangle is equal to this. Now, actually my first thought on doing this question was to sort of almost condition on the choice of the first rod, but you know, because we've got then the sort of the individual result in each of those cases here, but it's actually easier to think of this just as a combinatorics problem in general and kind of copy the style of proof from the previous question, and that's often the case in a step question. Actually, they sort of teach a method for doing something, and then you know the closer you can stick to that original method, you know, in the last part, if you can get to the answer, the better really. Although there will often be other methods that could be successful as well. So what we're going to try and do is say, okay, I'm just going to pick any 3 of these rods and see how many ways there are to pick 3 rods, and then see how many ways there are out of those that make the triangle, and then we'll turn it into a fraction for probability, and hopefully we'll get this formula. Okay, so right, so this time the number of ways of choosing 3 rods, right, this time it's going to be well, there's 2 capital M plus 1 rods, and we're going to choose 3 of them. So this time 2n plus 1 choose 3, so 2n plus 1 factorial divided by 2m plus 1 minus 3, or 2m minus 2 factorial times 3 factorial. So we get some cancellation here, so this is 2m plus 1 times 2m times 2m minus 1 over 6, and everything else cancels. And I guess I can cancel a 2 while we're here as well. So we've just got 1/3 times m times 2m plus 1 times 2m minus 1. And something nice has happened already, and I can see part of this formula. So I feel like I'm on a pretty good trajectory now. But we've got to do the harder part, which is, okay, how many ways are there that give acceptable triangles? And this whole question has split into the even and the odd cases, and so this is going to continue here as well, right? So obviously we are going to be thinking about the different cases. So we are sort of conditioning on the largest rod here, right? So I'm going to think about the number of ways of doing it where the largest rod is of length 2m plus 1, of length 2m, of length 2m minus 1, etc. But I'm going to think of all of the odd ones together, right, and the even ones together. So how many ways are there of doing it in the odd case, right? Well, it's going to be the sum from k equals 1 to capital M of k times k minus 1, right? Because what I'm doing here is I'm running through this k up to m, right? And in each of these odd cases, right, so for k equals 1 to m, right, 2k plus 1 gives me an odd number, which is, if you like, actually, if I called this n, this would be exact, instead of k, it would be exactly the n from before. And our result for the number of triangles was in terms of the small n, not the capital N. So I do want to just add up k minus 1, right, which is just the answer we got right back at the beginning here, n minus 1 for the odd case, right? And that will give me all of the possible triangles where the largest size is an odd number. Right, and in the even case, I do the same thing there, and I do k equals 1 to m, and this time I'm thinking of the 2 times k case as we had before, 2n, and in that case we got that k minus 1 squared, or n minus 1 squared as it was then, was the number of acceptable triangles when the largest. So this is the number of acceptable triangles when the largest rod is of length 2 times k, running from the first one of size 2, 4, 6 all the way up to 2m. Of course, the first ones here are actually 0 in these sequences, right? Because if the largest rod is of length 2 times 1, then I put in 1 minus 1 here and get 0. Can't make any triangles in that case. But there's no harm in keeping it in here. It doesn't break the sum. I mean, you could start here from 2 if you wanted to, and it wouldn't be wrong. You get the same result. But I'm going to leave it in the terms that it's here. So in total, right, I can just add these sums together. Because they're both summing nicely from k equals 1 to m, and then we multiply out and I get k squared minus k, and here I'm multiplying out k minus 1 squared, I'm going to get k squared minus 2k plus 1. So this is the sum from k equals 1 to m of 2k squared minus 3k plus 1, and they've helpfully in the question here given us the sum for the squares of the first n natural numbers, and you should be familiar with that from your studies, but I guess perhaps no need to memorize the formula then if they're going to give it to us in the exam. So I get 2 times this formula for k squared, so that's 1/6 times, now my summation goes up to capital M here, so that's m times m plus 1 times 2m plus 1. Right, and then we've got minus 3 times the sum of the first m natural numbers, as we talked about this before. That's just a half times m plus 1 then, and then summing 1 from 1 to m just gives us m. Now we just need a little bit of algebraic dexterity here, so the best thing to do here is to pull out the sixth here. We don't really like that I've written 2 1/6 like a mixed fraction here, but we know that means 2 times 1/6. Right? So I'm going to pull out a sixth and then multiply out. Oh, and I'll also pull out a capital M. So let's put that on the top here. So m over 6. And so that gives me m plus 1, 2 times m plus 1 times 2m plus 1, so that's 2 times 2m squared plus 3m plus 1. I've pulled out a sixth, so I need to multiply this by 3, so I'm going to get minus 9m squared minus 9m. And again, I've pulled out a sixth here, so this is going to give me a 6m here. So actually, let me write that as 1/6 m. So I've got, oh, and sorry, this is not, I've pulled out the m as well here, so this is actually m, this is there's no m's here and here, right? So, sorry about that. Okay, so, right, so we get this. So actually here I get 4 times capital M squared, I get 6m minus 9m, so that's minus 3m. I get plus 2 plus 6 minus 9, so that's minus 1. And then this factorizes as 4m plus 1 times m minus 1. And if you don't spot that, you can probably also work it out from the form of the question, right? Because we're given the answer here. Right, so hence the number, that's the number of acceptable triangles. So hence the probability that we get a triangle that is that it's possible here, or the probability that a triangle is possible, given the 3 rods that we've chosen, is the number of acceptable triangles, 1/6 m times 4m plus 1 times m minus 1, divided by the total number of possible choices here, which is this formula here, 1/3 times m times 2m plus 1 times 2m minus 1. And now you see we can cancel the m's and multiply top and bottom by 6 here, and we get the m's cancel, so we get 4m plus 1 times m minus 1 divided by 2 times 2m plus 1 times 2m minus 1, and that's exactly the form that's required here, and so we are done. So quite a nice step question there, and quite a classic one in a way. It's given us a first part here where it's sort of not an easy question by any means. There's some thought here, but it's really just warming us up into this way of thinking about the problem and just doing some counting. So it's not necessarily the fastest part of the question, but it's very important to, in fact, it's very important to do this part reasonably slowly, I think, so that you really understand what's going on in the question. Really, I've set up everything in the first part of this question with the pattern spotting and preparing for the harder parts, right? Then, it's gradually building up what is a tough problem-solving question here, right? So they've really then split it up into these even and odd cases. We've had to link the combinatorial idea to this geometric idea, but basically, once we notice the problem is the same one, we can forget anything about the triangles here, really. You should probably write a little sentence in here about why the problem is the same as the number theory problem, if you like, or the combinatorics problem here is the same as for the triangles, as just for choosing the numbers. And then finally put it all together in this harder final part. So I hope that was useful. Good luck if you're doing the STEP exams this year, or maybe next year, or whenever you're watching this video. And do check out the Mathsaurus website, where I've put a lot of past papers. I put all the grade boundaries for the STEP papers, and you can see all of the videos I've made for different questions for different papers there, organised much more easily than here on YouTube. Okay, so that's it for this video, and I will see you in the next one.